Before a building is framed, its circulation paths require rigid mathematical definition. Every ton of concrete and steel poured is bound by strict dimensional limits. We are going to deconstruct the functional geometry of a standard single-flight staircase, tracing how basic arithmetic scales up into a complete structural system. This grid starts with the atomic unit of staircase design. Here we have a single 6-inch vertical line. Branching from its base is the corresponding variable, a 12-inch horizontal tread. Together, they complete the profile of one individual step. This specific 6:12 ratio provides a gradual, ergonomic ascent. It aligns with the natural gait of the human body moving between floor levels. While these two numbers appear modest, locking them in instantly restricts the surrounding architectural blueprint. Selecting a 6-inch riser sets a rigid geometric baseline. It dictates the boundaries of every subsequent structural decision required to connect two floors. To bridge vertical space, the single step must multiply. The initial 6:12 profile duplicates and arrays diagonally, creating an uninterrupted path between floors. Accumulating these 6-inch vertical increments establishes the total rise. Simultaneously, the sum of the 12-inch treads locks in the physical footprint on the ground, the total run. This creates a fixed, unyielding diagonal grid cutting through the flexible empty space of the building. Holding this diagonal grid in midair requires an underlying structural mass, a base slab capable of supporting live dynamic loads. Before any steel is modeled or concrete poured, the absolute physical boundaries of the entire system have been permanently defined by the basic arithmetic of one riser and one tread. The relationship between the total rise and total run is governed by a mathematical constant, the stair pitch. We calculate this pitch using basic trigonometry. The triangle beneath the flight shows tangent theta equals rise divided by run. Substituting our dimensions gives 6 divided by 12, or 0.5. Taking the arctangent reveals an exact angle of 26.6 degrees. This 26.6 degree pitch is the unalterable mathematical reality of a 6:12 staircase configuration. Yet, a recurring professional conflict exists in structural drafting. Standard drawing notes frequently request a nominal 30-degree reference angle of repose for staircases. A requested 30-degree angle mathematically contradicts the proven 26.6-degree geometry of a 6:12 stair. They cannot both physically exist in the same space. Blindly enforcing standard drawing notes without checking the underlying trigonometry of the actual step dimensions guarantees physical clashes during construction. If an engineer forces the design to meet that requested 30-degree pitch, the physical structure has to warp to accommodate the math. Because the 6-inch riser is bound by strict floor-to-floor elevation requirements, the horizontal tread is the only variable left to absorb the change. Watch the geometry. As the slope steepens to 30 degrees to satisfy the drawing note, the horizontal tread space must compress. To hit exactly 30 degrees with a 6-inch riser, the tread shrinks from a comfortable 12 inches down to 10.4 inches. A 10.4-inch tread leaves inadequate surface area for an adult foot, severely compromising human safety and balance during descent. Engineers resolve this by retaining the 12-inch tread and accepting the 26.6-degree pitch in construction. The 30-degree specification is treated strictly as an idealized reference, not a geometric command. The functional geometry of the human foot dictates the design, overruling standardized angles on paper. With the theoretical geometry resolved, the focus shifts to the physical materials required to bear the load. A transverse cutaway exposes the internal layers of the staircase assembly. This cross-section shows the primary load-bearing element directly underneath the steps, the reinforced cement concrete, or RCC, stair slab. The slope and uniform thickness of this slab are completely dictated by the 26.6-degree pitch we calculated earlier. The slab acts as a continuous structural member, locking into the horizontal floor levels at the top and bottom of the flight to transfer the dead and live loads away from the stairs. The exposed concrete edges of this slab also provide the necessary anchor points for the structure's safety infrastructure. The RCC slab bridges the abstract mathematical coordinates and physical mass, functioning as the load-bearing spine of the system. Every open edge of that concrete slab requires a safety barrier to protect users. Looking at the elevation, we add a steel railing system that must seamlessly follow the 26.6-degree pitch of the RCC slab. The primary specification calls for continuous mild steel pipe for both the handrails and the vertical supporting posts. To prevent lateral movement, a rigid structural pattern connects those vertical posts. X-bracing constructed from solid mild steel round bars is welded into the gaps, providing high shear strength and visual balance. Translating this pattern into physical fabrication requires examining the individual components. This panel isolates the specific cross-sections of the railing members. It clearly defines the hollow pipes versus the solid round bars used for the X-bracing. While the 26.6-degree pitch determines the layout, the precise pipe diameters and wall thicknesses are engineered against specific load requirements. The completed railing acts as a rigid envelope, perfectly calibrated to match the unyielding geometry of the concrete foundation below it. A single 6-inch line scales upward into a comprehensive structural system. This is the result: the elevation, the RCC cross-section, the steel profiles, and the precise trigonometric calculations integrated into a single unified technical document. The 6-inch riser is the primary variable. It establishes the total run, dictates the exact slope, and defines the steelwork boundaries. When properly calculated, that 2D blueprint translates flawlessly into physical reality on the active construction site. Resolving drafting discrepancies on paper, like verifying an actual 26.6-degree pitch against a 30-degree reference note, prevents cascading, expensive failures during fabrication. Structural integrity relies on the rigorous verification of fundamental geometry by a qualified engineer, ensuring every physical connection aligns precisely as calculated.